Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to discuss about the procedure for shear design of reinforced concrete beams. So the very first step is to plot the exact or ACI code shear force diagram for the beam. So we can plot the shear force diagram of the beam by using the analysis method that we have studied in the analysis subjects. For example, if we have a simply supported beam subjected to a point load, then its shear force diagram will be like this. So this is its exact shear force diagram. Or if we have a continuous beam, and in that case the exact shear force diagram will become a difficult one, so we can use the ACI coefficients to draw the shear force diagram for such beam. So ACI coefficients for the supports, exterior support, interior supports, and for the different end conditions the ACI coefficients are given, so we can use those coefficients to draw the shear force diagram. So also draw bending moment diagram if the exact equation for VC is to be used. So if we use the exact equation for VC to calculate the shear resistance of concrete, so in that case we also need V and M. So for that we need to calculate the moment as well at the section for which we are going to calculate the shear reinforcement, or for which we are considering the maximum shear force. Okay, the second step is find maximum design shear VU and factor moment MU at the critical section. And in case of shear, the critical section is normally at distance D from the inner face of support, but it can be different as we have discussed in the previous videos. Okay, calculate the concrete shear strength, preferably by using the exact equation, which involve the longitudinal reinforcement as well as the moment at that section. However, if the data for exact equation is not available, for example, if we don't know the bending moment and the longitudinal reinforcement details, so then we can use the approximate equation given by the ACI code, which is 0.17 square root FC prime VWD to calculate the VC, shear capacity of concrete. The next step is to check whether the shear reinforcement is required or not. If the applied shear is less than the design shear strength divided by 2, so in that case no shear reinforcement is required. However, we can provide the minimum stirrups to keep the longitudinal steel in position. And after that we need to calculate the shear resistance that need to be provided by the shear reinforcement Vs, and it will be equal to Vu minus 5 divided by 2, and this is divided by 5, and this will be in the case if Vu is more than 5 divided by 2. So if Vu is less than 5 divided by 2, so in that case no shear reinforcement is required, so in that case this Vc will be equal to 0. And if this Vu is more than 5 divided by 2, so in that case the Vs, or the shear resistance to be provided by the shear stirrups, can be calculated by using this expression. After checking whether the shear reinforcement is required or not and calculating the shear resistance to be provided by the stirrups, the next step is to check whether the size of the beam is okay or not. So if the Vs is more than 0.33 square root FC prime BWD, so in that case we need to revise the section. So either we need to increase this BW or we need to increase the depth of the beam. But in some cases we can increase this factor up to 0.66. We can double this value. Okay, the next step is, after checking the size of the beam, the next step is decide a trial diameter and shape of the stirrup and calculate AV. So we need to decide the diameter of stirrup. For example, it is number 10 or in US customary number 3 bar. And the shape of stirrup, whether it should be a double leg stirrup or it should be a triple leg stirrup are 4-leg stirrup. So we need to decide the shape of the stirrup, and after deciding the diameter and shape, we can calculate the AV, which will be equal to area of bar times the number of leg. Okay, the next step is calculate the required spacing using the following equation and compare with the maximum and minimum allowed values. So we can see the maximum and minimum allowed values from the code, so as we have discussed in the previous videos. And to calculate the spacing, the required spacing as required, so we can use this expression. This is 5V AV FY TD over VU minus 5V VC. This is actually comes from Vs is equal to AV Fy D over S. So after rearranging this equation, so if we bring S over here, so it will become AV Fy D over Vs, and Vs is equal to actually Vu minus 5Vc divided by 5V. So after substituting the value of Vs, so this relation will become this one. Okay, so after that, the next step is round the calculated spacing to the nearest 10 millimeter multiples. So we will calculate the required spacing and compare it with minimum and maximum values, and then round it to the nearest 10 millimeter multiple. And always we need to round down this value. For example, if we got the value of 98 millimeter, so it will be rounded down to 90 millimeter instead of 100. So if this value is lesser than the minimum value, which is 80 millimeter, so in that case increase the number of leg of stirrups if possible, or yield strength of stirrup if it is possible, or the diameter of the stirrup, so that the required spacing is more than 80 millimeter. So up to here the design process is completed. So next is detailing. So in case of detailing, we need to place the very first stirrup at a distance s by 2 from the inner face of the sport, and decide how many such stirrups are to be provided or to be continued toward the center of the beam. So if we have beam like this, and here we have a sport, so the very first stirrup will be provided at a distance s by 2 from the face of the sport, and then the next stirrup will be continued at a spacing s, and we need to decide how many stirrup we need to continue toward the center of the beam. If this is the center of the beam, then how many such stirrups we need to provide. So usually the spacing for the most critical section is continued up to a distance in between ln by 4 to ln by 5. So for example, if we have this beam and it is simply supported, so in that case the shear force diagram will be like this. If it is subjected to UDL, so the most critical section will be at a distance d from the face of the sport, and we need to decide the spacing of the stirrups corresponding to that section, and then we need to continue this spacing up to a certain distance, and this distance should be ln by 4 or ln by 5. So up to this much distance we need to continue this spacing that has been calculated for the critical section, and after that we need to recalculate the VU and MU value at the new section and calculate the new spacing of the stirrups, and then we need to continue that spacing toward the center of the stirrup up to a new location or up to a point where there is no stirrup required. Okay, calculate VU and MU at this new location, I mean ln by 4 or ln by 5. So it is to be noted that the spacing may be recalculated after placement of each stirrup if the construction is carried out in the factory. So if the construction is carried out in the factory, so in that case we have controlled conditions, and we can use the computer programs to calculate the spacing of the stirrups, and that spacing or that member is actually replicated many times in the factory, so we can have the benefit of economy if we calculate or recalculate the spacing after each stirrup. But in case of construction, in situ construction, so in that case this will not be a good option, because there will be a lot of chances of errors, human errors, during the placement of the stirrups. Okay, so repeat the step 3 or step 2 to actually onwards, leaving the irrelevant steps to calculate the spacing up to the point where no shear reinforcement is required, or make calculation for one more point in between. So initially we calculated the stirrup spacing at this location and provided up to this one. Now calculate the stirrup spacing for this location and provide up to this one, and then calculate the shear spacing, a shear spacing for this section, and provide up to the point where no further stirrups are required. So the location beyond which shear stirrups are not required by the ACI code can be approximately found by equating the expression for the external shear in terms of distance from the support X to VU phi C, from the support X to phi V VC divided by 2, using the approximate relation for the concrete shear strength. So in that case, what we can do to calculate the location where no shear reinforcement is required, so we need to compare this VU, the applied shear, it should be less than equal to phi VC divided by 2 for the condition that no shear reinforcement is required. So we can say that VU is equal to phi VC divided by 2, and from to calculate this phi VC or VC, we can use the approximate relation 0.17 square root FC prime BWD, because at that location we don't know the actual value of the moment. And for VU we can write the equation in terms of X. For example, if we have a simply supported beam subjected to a uniformly distributed load W, so its reaction is, for example, R, so it will be R minus Wx. So this will be our equation for the shear force VU, and we need to equate it with this one, and from this equation we can get the value of X.